And centripetal was a Greek word meaning center seeking. Okay. The idea being here, and today we're going to extrapolate this to, like, say, planets. Say you have a planet that's going around the sun in a circle. The planet would normally want to travel in a straight line and just go flying off into space. Which actually, from a, like, human living point of view, if Earth were to change its trajectory, we wouldn't last very long, because Earth is like at the most perfect place it could possibly be. We're not too close to the sun that we'd burn up and die, but we're not too far away from the sun that we'd freeze to death. If that makes sense. But if Earth were to somehow end up like its orbit, wherever Earth is right here, if Earth were to somehow start orbiting here instead, we probably wouldn't be able to sustain life. Anyways, that's probably not relevant here. The idea I was going for is that ideally things going in like circular motion, really their velocity is going at a tangent. Why does this thing not go that way? Well, because a center-seeking acceleration, or a force, because really forces and accelerations go together, pulls it to the middle, drawing it back in, so that when it's trying to go this way, really this thing was getting pulled into the middle, if that drawing makes any sort of sense, so that the velocity could then change.
A question.
Yes?
Would that centripetal force in this case be gravity?
Good, and that was going to be my next point here. Centripetal force is typically the net force, and we worked with net force a lot in the last unit, but the only force in this particular example would be gravity. And so we could actually say that the centripetal force, which is usually like either m v squared over r, or m 4 pi squared r over t squared, you can use either of those formulas, that would be equal to your force of gravity. And that's actually what my next slide is on. I actually wrote that down here. Let me go through the stuff. I don't want to actually skip anything here. Okay, I mentioned in the last unit, this is my opinion, I hope you share it with me, but that discovering the capital G constant was one of the biggest breakthroughs that physicists have ever had. And I have a couple of reasons for that. One, because of that, we can predict the mass, the radius, and the gravitational field strength of different planets. That's huge, because going to the moon, it helps knowing that gravity on the moon is going to be about 1.62 meters per second squared. You can then plan for that and know that you're going to be like bouncing. Okay? I've heard this before. When NASA was trying to send their first landers to the moon, one of their biggest issues was making sure that the lander actually landed on the moon and didn't actually hit the moon, bounce off the moon, and go hurtling back into space. Does that make sense? And the issue for that was, well, there's way less gravity on the moon. And so that's actually a realistic possibility. Let's say you were trying to do that on a heavy planet like, I don't know, Jupiter. That won't be a problem on Jupiter, because Jupiter has so much gravity that you might not even survive, because it's going to be crushing you into the planet. That makes sense? Maybe. Well, or we need to build stuff that's capable of withstanding that sort of force. Any of you guys followed the news recently and hear about this comet? Was it a comet? That NASA managed to land a rover on? Anyways, it's been in the news recently. They found a comet and they landed a rover on it. And we're taking some samples. And it's the first time they've ever done that before. And that's what I want to talk about today. Because of calculating G, we were also able to calculate the speed at which planets are moving and predict their motion. Let's say we want to land a rover on Mars or the moon or a comet. Okay. Let's say Earth is over here and you send your rover off in this direction right here. How useful is that if Mars is actually way over here? We have to actually like time it so that this guy and this planet, they actually collide at the same time. Does that make sense? Because if you miss by a little bit, the planet is traveling, you're traveling, whoops, I missed. And I'm not even doing this properly because really it's in 3 dimensions, right? So we're not even talking just like this. It could be like this. They actually would have been at the same spot here, but there's a gap between my fingers. So there's a lot of calculations here. And that's my goal today is we're going to try to figure out how fast planets are actually moving at. Make sense? So, here's how we'd go about doing that. This is what Hannah was suggesting. Our centripetal force is our only force. Keeping a planet moving is, well, sorry, gravity is the only force keeping our planets from like flying off into space. Okay. Well, that's your centripetal force. Well, we can then calculate a velocity by making kind of our own equation and rearranging. Because here's a formula for centripetal force. Here's a formula for gravity. How could you get velocity by itself? Okay, let's start by moving R up. So now R would be up here. Here's something interesting. Now you have R up here, and 2 R's down here. Yeah, one would cancel. And then you'd have to divide by mass. Now, what would this mass be of? Okay, so is it the mass of the object orbiting or the object being orbited? Let me actually give you a better word for it. We call them a satellite. Okay, the object that is going around in a circle, pardon me, the technical term in physics for it is a satellite. Okay. Now, you guys have probably heard the term satellite before and you think like, I don't know, what we use to like get TV signals to work. Okay, that is a satellite, but satellite in physics encompasses anything that's orbiting another planet, basically. So the moon is actually a satellite of Earth, and the Earth is actually a satellite of the sun. If that makes sense. So this M right here then is the mass of whatever is orbiting, which is a satellite. So when we divide this mass away and divide this mass away, one of these masses can cancel. Which mass then is the one that you're left with? Yeah, the planet, basically. This mass right here will be the mass of the actual planet itself. So if we want to find a velocity, then you got to square root. So velocity is going to be equal to big G times the mass of your planet divided by R, all square rooted. Does the mass of the satellite matter? Apparently not. I feel like this is very useful. Like I said, if we're trying to figure out a way to land a rover on a comet, all we have to do is figure out what it's orbiting. We know capital G now. We got to figure out its radius, and we got to figure out the mass of whatever it happens to be orbiting, the sun, the moon, whatever. And then we can figure out how fast it's hopefully going. Using that speed, we can then hopefully try to make it so that our ship and it meet at the exact same place. That makes sense? Okay. Now let's do some examples then. So let's figure out how fast a satellite moves above the Earth with an altitude of 260 kilometers. Good, yes. We're going to need units to be in kilograms for mass, meters for any sort of distance. So, we could just probably go right to this formula here, the V equals G, it's capital G, mass of your planet over R. Okay. By the way though, this formula is not on your data sheet. So if you ever forget how we achieved it, just remind yourself that it was achieved by making FC equal to FG and doing a whole bunch of rearranging. So, capital G, 6.67 times 10 to the minus 11. Okay, what are the units for this again? Newtons, meters squared over kilograms squared?
Yeah.
Nice. Mass of planet. Earth, so 5.97 times 10 to the 24 kilograms. Okay, gotta be careful on this one here. Radius.
Wouldn't that be radius plus?
Well, it'd be the radius of the Earth plus the fact that it's above the Earth's surface. So what is it? 6.37 times 10 to the 6 meters. And then this 260 kilometers, we got to put that into meters as well. So then make it 260,000 meters. And when we're done, we're going to square root it. Divided by bracket 6.37 times 10 7,000 square root. I got 7,749. Same thing? Okay. Make sure you watch SigDigs, by the way. I just handed back assignments. I felt like I was writing SigDigs way too often in terms of questions there. My standard was to take off a half mark if I ever saw a SigDig problem. Sometimes I forgot, so if you somehow managed to escape losing a half mark, you got lucky, I think. But for the most part, I was taking a half mark off if you ever forgot a SigDig. Because please stop forgetting that by now. We're in November. So, okay, so we gotta get SigDigs right here. How many do I get? Yeah, 3, 3, 3. Everything's got 3 numbers basically. So 7.75 times 10 to the 3 meters per second. Do I need a direction? This is a centripetal velocity. And so really we can't do a direction because it's just going around in circles. Right? Sometimes it's going this way, sometimes it's going this way, sometimes it's going this way. Like it's always changing direction. No, inward is when we're talking about either acceleration or force. But for the actual speed slash velocity here, we really can't pick a direction because it's always changing. To be honest, it gets even worse in space. I mean, there's no north, south, east, or west in space. There's no up or down. Does that make sense? So that makes it even more confusing because, I mean, where's your frame of reference? Which way is up? There is no up. So, did that make sense? Okay. The point I want to make with some of these examples here is that the formula we used, not on your data sheet. You may need to actually like jury rig and like piece together your own formula sometimes by basically taking your centripetal force and making it equal to some sort of other force. Today, typically that force is going to be gravity. Okay. Here's my second question. Let's take that exact same satellite. My question now is, how long will it take for it to orbit the Earth? What am I asking you for? Period. Yeah. So we need to find some sort of formula that involves period. Let me go back to our formula sheet. That's kind of why I wanted to start there. Anyone see anything on here that's useful for solving for period? Okay, well let's pick out all the formulas that involve period. Here's a formula that involves period. Is that an effective formula for us? That involves period of a spring, so that's out. Here's a formula that involves period. That's for a pendulum, that one's out. This involves period from frequency, but we don't really have frequency either, so that one's out. Where else do I have period then?
Acceleration.
Okay, how about this guy right here? Do we know the velocity it's traveling at? We just calculated it. Do we know the radius at which it's traveling? We have that. So we could use this formula. That's one way of doing it. There is another possibility. It might be a little more work, but you know how we did Fc equals Fg? Rather than using Fc as mv squared over r, we could have done m 4 pi squared radius over t squared equals g m1 m2 over r squared. We could have done this instead and isolated for period. Rather than using like this thing, rather than using v squared over r, we could have used this guy. But it's probably most effective just to use this formula now. So just make sure we can do that. Where are we up to? Okay, so velocity centripetal is equal to 2 pi radiuses over a period. How do I get period by itself? Just swap VC and T, right? So 2 times pi. Our radius was, what was it? 6.37 times 10 to the 6 plus the 26 whatever kilometers there. And then what velocity did we just calculate? It was, we need to use that exact velocity though if we can. So I believe it was like 7,749 point something. Wrong value?
Yeah.
Okay. So this number here, the 774985, I'm going to use that value. I'm going to go 2 times pi times 6.37 times 10 to the power of 6 plus 260,000. And then I'm going to divide by that exact value. Anyone else get this? 5,375?
Yes.
Okay, interpret that though. What units is that in?
Seconds.
Yeah, seconds. So 5,375 seconds. Why don't we put this in a more reasonable unit? If I divide by 60, it would be minutes. That's probably a more reasonable number. Apparently this thing goes around the Earth every 89.6 minutes. Yeah, hour and a half. Keep in mind, that actually kind of makes sense. This thing is traveling at 7,000 meters per second. In terms of perspective, if you're driving on the highway at about 110 kilometers an hour, you're going about 30 meters per second. It's about, like, I think 25 is 90. So yeah, like about 30-ish meters per second, 28 meters per second when you're driving that fast. This thing is traveling 7,000 meters per second. It is hurtling through the air with a lot of speed. So, I mean, it is going around the Earth fairly quickly. All right, any questions so far? Okay. Okay, I need to introduce to you now what are called Kepler's laws. Scientists, we've figured out some math behind how we think these things should travel, but there were some problems. Okay, I'm going to tell you like some history here. Scientists for years had known about stars and planets. Astronomers would plot the paths of stars in the sky using observatories for like thousands of years. They always followed stars. Okay. However, there was a problem. Mars did not seem to follow mathematical predictions. So like they did a whole bunch of calculations. They thought Mars should be doing this, and Mars was always slightly off. And they could not figure out why is Mars not quite in the right spot. That makes sense? So here's also one of the weird things. Some people still at this time were still thinking that the Earth was actually the center of the universe and the sun and stars went around the Earth. So I mean, they were flawed because they didn't realize that sun, Earth goes around. They thought it was Earth, sun goes around. Okay. Kepler, the guy I'm introducing today, he had 3 ideas about planetary motion that are probably true, we can say, at this point here. So one of his ideas was that planets actually are not circularly orbiting something. They actually orbit with slightly elliptical paths. Do you guys know what an ellipse is? It's a slightly squished circle. Yeah, an oval is a good example. This is an ellipse. Okay, an oval is probably the best example actually to use. Now, planets are slightly elliptical. We're not talking by a lot. This is a huge exaggeration. Okay, but like imagine that I were to try to draw a perfect circle. Is that going to have like the exact same radius everywhere? And the truth is, well, it probably doesn't. I mean, it looks like a pretty decent circle, but it's probably not exactly a pure, perfect 100% circle. Does that make sense? And we've discovered that planets also follow not perfectly circular paths. Darn close, but not perfect. Does that make sense? It's another assumption we actually have when we talk about planets. What shape would you say a planet has as like a 3-dimensional shape? You'd probably say like a sphere. But again, actually not all planets are perfect spheres. I mean, are they close to a ball? Sure. But are they perfect? No. Okay. So here are Kepler's 3 laws. First law, the path of an object in an orbit follows the shape of an ellipse. Okay. And one of the orbited body is at what's called a foci. You guys ever heard the term foci before? Okay. It's kind of like the center of a circle, only with it being an ellipse, there's 2 centers to the circle. Okay. Here's like one center to like kind of a circle right here, and then here is the center of like a second circle right here that kind of like merge together to form one large circle. I don't know if that makes any sense at all. Okay. Maybe the 2 circle thing doesn't really fit. So like here's a planet. This could be the sun. Okay. The Earth actually pretends that there's like an actual sun right here. There's actually like a second point right here. That's almost like a second like center of a circle. It's not actually a circle, but these 2 points right here are called foci points. Focus. If that makes any sense. It's not really relevant for what we're solving here. Okay. Long story short, they're almost circles, but not quite. Second thing Kepler discovered. If you were, this is really weird wording, by the way, so I'll try to put it in people words in a second. If you were to draw imaginary lines from the sun to the planet, it sweeps out equal areas in equal times. Okay, in people words. This is an area right here. This is an area right here. The area from here to here should take 15 days. The area from here to here should take 15 days. That's what he's suggesting. But what it impacts is the speed. The speed along this axis is going to be way faster than it will be on this axis right here. It's kind of like a slingshot. As the planet goes around this guy right here, it slingshots around, and you actually get a faster velocity on this side than you do on this side, was his hypothesis. The reason being is over here, you're actually closer to the sun, and over here, you're further away from the sun. So over here, you'd have a higher velocity, and over here, you'd have a slightly lower velocity. Now, it's not by much. I found this picture on the internet. Here's a picture of an elongated ellipse. Like, it's nowhere near this bad. Like, the Earth goes around the sun almost in a perfect circle. But, like, I'm exaggerating in this photo. But they've discovered that when you're close to the sun, Earth actually travels at 109,000 kilometers an hour. But when you're further away from the sun, it's only 106,000 kilometers an hour. Yeah, it's still really fast, obviously. Okay. The idea basically being, have you guys ever heard that term slingshot used to describe like how they try to get like objects to travel in space? Okay. The idea being, if you can get it to kind of go around the sun like this and circle around, it actually picks up a lot of its velocity right here, and the velocity actually increases on this side over here. And then usually what they do then is they engage the thrusters at this point and then try to break away from the orbit, and then you have a lot of speed in order to travel off to your next destination.
Is that just like the fact that like you're closer to the sun and
Yeah.
closer to gravity?
Yeah, exactly. You're just slightly closer. Therefore, you have like just a little bit more speed on this side than over here. Here's his third law, and this is a formula that's not in your data booklet. So maybe write this down somewhere. Kepler discovered the square of the orbital period dividing by the cube of the radius is equal to a constant. Good old constants. Another leading coefficient out there. I don't know why they didn't throw this in your data booklet, to be honest. Doesn't make sense to me. So here's the formula. A capital K is equal to t squared over r to the third. Okay, here's some notes I have on this. According to SI, have I ever told you guys what SI stands for? Yeah, metric basically. It's System International. It's like French. Metric units basically. The units for this should be seconds squared over meters cubed. These units are so completely irrelevant. Like the actual number here is not all that useful. Just the idea that it's a constant is useful. Typically though, we don't work with seconds over meters all the time. You could go with years over kilometers if you want to change the units up. Here's a table that involves information for all of the different planets in our solar system. Plus actually a couple things that are not planets, like poor little Pluto.
What's that?
I believe that is a moon off of, I have it on another example here, I think. No, it's a moon of one of the planets. I forget which one it is. Okay. Because a lot of these units get really large. Sorry, let me go back a slide. Sorry, I'm making you flip everywhere. What I really want to look at is these numbers right here, the radiuses. These numbers here are all very large. And sometimes rather than working with very large numbers, it makes more sense to like reduce and talk about it in like terms of like, you know how like 12 doesn't 12 dozen, 12 means a dozen. Does that make sense? And if you guys are taking chemistry, a mole is 6.02 times 10 to the 23. Okay, we kind of have the same concept here. Rather than work with some of these really weird numbers, scientists came up with another idea. Let's call distance an AU. AU stands for astronomical unit. 1 AU then is how far it is from the Earth to the Sun. So then whenever I ask you how far is it from the Earth to the Sun, you say 1. That is a lot more efficient than saying 1.49 times 10 to the 11. It just means that everybody else then gets compared to that distance. So if I go back to this chart here, if Earth is defined as 1 for AU, then Venus and Mercury are more because they're closer. And all of these guys are more. Did I say that backwards?
Yeah.
Having a bad day. These guys are less because they're closer. And these guys are more because they're further away. So like this number right here means that Neptune to the Sun is actually 30 times further away than the Earth is. Does that make sense?
30
Yeah, times more further away. So the reason why this was developed though is when we work with what's called that Kepler's constant, rather than using weird big numbers, this was decided to be way more efficient. The top is supposed to be your period. Well, how long does it take the Earth to go around the Sun? 1 year. Square 1, still 1. How far is it from the Earth to the Sun? 1 astronomical unit. So then what's the K value for the Earth around the Sun? 1. So it just makes it a nice easy constant to work with, rather than something stupid like 6.67 times 10 to the minus 11. Does that make sense? But if we wanted to, we could have used 365 days squared over 1.49 times 10 to the 11 meters cubed, and also found that K value. But doesn't this seem kind of ridiculous to do all that math and find some stupid number when we can make the value be 1 instead? So let me show you an example of a question here then. We know that Neptune goes around the Sun every 60,000 days. It takes a long time for Neptune to go around the Sun. 60,000 days. So my question is, how far is it away from the Sun? Okay, so here's how you might go about solving this. Okay. My question was, first let's use Earth's data to solve for K around the Sun. But we already did that. What is the K value for the Sun? It's equal to 1, with 1 being the product of 1 AU squared over, what was on the bottom again? No, I'm backwards here. It was 1 year squared over 1 AU cubed. So what we need to do now is convert everything of Neptune's into either
Mr.
years
Forster, can you please come to
or
the office?
astronomical units.
Mr. Forster, please come to the office.
So how many years is this number here? So if you take 61,090 and divide by 365, oh my goodness. 164 point. Thank you. So then what you could say then is 1, because that's that K value, is equal to 164.904 squared divided by the number of, what do I call it, X. And I'm going to solve for how many AUs there is. I'll have to do that as well, so I'll have to cube it as well. So then to get X by itself, I'll just swing X to the side and say that X cubed is equal to 164.904 squared. And then cube root both sides. $61.90 divided by 365. Oh, stupid calculator. Okay, 6 36190 divided by 365. And then we're going to square this number. And then we're going to cube root this number.
Sorry.
Okay, is everyone able to calculate this 30.07 number here?
Yeah.
Okay, can I talk about a couple things here first? What units is this in? AUs, okay? Because if this was in years and this was in AUs to make it simple, then when we do all of this rearranging for Neptune now, this will be in years, which we had to put it into years. And then this X value that we solved for will be in AUs. Okay, so this is how many astronomical units it is. By the way, if we go back to that chart, it's really close to that same value. The only reason it's slightly different is that technically Earth doesn't go around the sun in exactly 365 days. It's actually like 365.24 days. So it's like slightly out. So we have leap years, if you didn't know that. We have to have an extra day every couple of years. If I wanted then to figure out the distance in meters, I would have to take this 30.07 AUs, and I'd have to multiply by the ratio, which is 1.49 times 10 to the 11 meters in every one astronomical unit. And that would be how many meters it is from here to Neptune. So take that and times by whatever an AU is, 1.49 times 10 to the 11.
If you have the value in AUs, isn't it all relevant to calculating?
Well, this is how they were calculated, though. I guess, does that make sense? Like that chart there was developed based on doing these calculations. Because we obviously didn't like take a tape measure from here to Neptune and measure it, if that makes sense. So you're right. I mean, we probably don't need to do these calculations because we have the numbers now. Does that make sense? So the distance from here, no, the distance from the sun to Neptune should be 4 point, okay, sig digs now. When we did 365 days, that probably should count as our sig digs because 365 only had 3 probably. So let's go with 4.48 times 10 to the 12 meters. And hopefully that's very similar to what Neptune's distance was supposed to be. Slightly out though. Like I said though, that's because Earth doesn't actually go around the sun in 365 days. It's 365.24 something.
I don't understand why we use Earth's orbital radius to...
Everything that goes around the sun has the same K value. So the Earth, we determined Earth to make a K value for the sun of exactly 1. It means that everything else has to have that same K value of 1 if we're talking about the sun. That was Kepler's law here. Basically, the object being orbited, we don't care what it is being orbited. Everything that goes around it, the mass of the object, is kind of irrelevant. All that matters is the period and the radius. And so this value right here is the same for any object that you're working with that goes around it. So it could be for Neptune going around the sun. It could be just for a random asteroid going around the sun. That K value of 1 is the same thing. Here, why don't you guys take a 5-minute break and grab breakfast too? And I'll finish my last 2 examples.
Well, it was kind of fun because after
And then to get X back again,
two
we
teams
still
that
have
were
to
staying there, and then one us. So we all just kind of
answer.
like made teams.
We had the same answer, but maybe that was more confusing because there were ridiculous numbers. They decided, hey, let's just arbitrarily call this one. Does that make sense? Okay. Guys, let me try these last 2 examples and then we can call it a day. So I was just saying to Carlin here, I'm hoping I'm making this point well enough. The reason why this AU was developed was to make life easier, because rather than working with K values that are really stupid, we just made the K value equal to 1 for the sun, and that just made things a lot simpler. But here's an example where we can't do that. we're going to try to figure out how things work around this around Mars. Mars has 2 different moons. And we're going to try to use one of the different moons to find the k value for Mars. Once we find the k value for Mars, we're then going to use that to calculate the other moon. Let's say that one more time. We're going to use one of our moons of Mars to find Mars's k value, which, by the way, won't be equal to 1. Once we find that k value, we'll then use that k value to find information on the other moon of Mars. So let me give this a check. What we know is that this moon here, Phobos? Sure. We know its radius. We know its period. Okay. So if I want to find the k value for Mars, the k value for Mars is equal to, what is it again? I always got to remind myself. Period squared over radius cubed. I could convert this into other units if I really wanted to. And if that was somehow helpful, I would. But to be honest, it doesn't really matter. So let's make the units be 0.3189 days squared. And then the radius was 9378 kilometers cubed. And let's find this k value.
The radius is okay in kilometers.
Sure, it just means that when we solve our next half of the example, we have to keep the radius in kilometers though. So square that guy, divide by this guy cubed. So I got a k value of 1.233 times 10 to the minus 13. Does this k value mean anything? Not really. The number itself, completely irrelevant. All that matters is its units. Its units are days squared over kilometers cubed. So this is the value for Mars. Oh my goodness, I cannot spell today. This is the k value. Well, now I can say that that k value of 1.233 times 10 to the minus 13 for a different planet is equal to 1.262 days, all over an unknown radius cubed. How do I solve for that unknown radius? Divide by your k value, basically, right? Like take your x, swing it up over here, divide the k value away, and then cube root. So to get x by itself, maybe rather than calling it x, I'll call it radius, I guess. To get radius by itself, you need to take your 1.262 days, you need to square it, you need to divide by your k value of 1.233 times 10 to the minus 13, and then you have to cube root the whole thing. What units will this radius then be in? Kilometers. Why not meters? Well, because I didn't convert it to meters in the first place. So Sam, you asked me a while ago whether we had to convert to meters. You could. But I feel like what you'd end up doing is you'd convert from kilometers to meters, you'd do this whole calculation, and then you'd probably convert from meters right back to kilometers. So that's kind of a waste. So 1.262 squared divided by our k value. And then cube root it. So I got 23462. Anybody else get the same thing as me? 23462. So that's in kilometers. So let's go with 2. Get a lot of sig digs here, don't we? 4 sig digs. 2.346 times 10 to the 4 kilometers.
What did you get? How did you not get that?
When you divide, I divided by answer just to make sure that it worked properly. But if you were to divide by this number, you may want to put that number in brackets. When you divide by that, like this k value, you may want to put a bracket around it.
I actually got the key root it.
You got the answer you wanted then?
Yeah.
Okay. Does this answer make logical sense? Well, let me go back to this picture here. This first planet was about 9,000 kilometers away. This second planet should be more distance away. And it is, because this was 9,000 kilometers and that was 23,000 kilometers. So, I mean, in terms of context, it's good because it should be further, shouldn't it? Okay, second half of the question, what speed is it moving at? Yeah, we just need a velocity formula now. So the formula for velocity in a circle, because it is going in a circle, is equal to 2 pi. What's that math component from calculus? Radius over period.
Radius is what we just calculated.
The radius is what we just found. Only one issue here, though. We now do need to convert that radius into meters for this to work.
No, we have to convert it into
And period would need to be in seconds. So maybe as a bit of an aside here, if you have 23462.8 kilometers, if you times it by 1,000, because that would be 1,000 meters in a kilometer. And then, what was our period again? 1.262 days. Okay, so then 1.262 days multiplied by, what is it, like say 24 hours in a day, multiplied by 60 minutes in an hour, multiplied by 60 seconds in a minute. Times 24 times 60 times 60. Well, now this is in seconds though, right? So this is 109,036.8 seconds. You get the same thing as me for time here? Okay. And then for your radius, this should be 23462,800 meters. Because you're just adding 3 zeros. So 2 pi times 2.346 times 10 to the 7 divided by 109,036.8. Sorry, it's a mess. I'm gonna have numbers everywhere. 2 pi multiplied by, I can't go up and do that number there. 23462.81514 times 1,000, and then divide it by 109,036.8. 1352? Excellent. Sorry that it's kind of everywhere. So 1352 meters per second. So this thing isn't going quite as fast as that first satellite we calculated that was 7,000 meters per second, but it's still going pretty fast. So, I should do sig digs though.
Wouldn't you have to add the diameter of the planet itself?
Oh, you're right. We probably should be adding the diameter of the planet itself. No, that was already incorporated in this orbital radius. When we said orbital radius, that would have included it. Good point though. If I said altitude above the planet, then include the radius of the planet itself. But if I give you orbital radius, that implies that we've already calculated that. Thank you, Jack. That's a good catch.
So you're just saying that's the radius of the planet plus.
Yeah, so like when it's set up here, it had an orbital radius. That means that like it is from the center of Mars to the center of Phobos.
Okay.
It already has calculated that. So we don't actually have to try to add the radius of Mars itself or the radius of Phobos itself. That's already been done for us. Otherwise, if it said the altitude above Mars, then you'd want to probably add that amount on. Okay, sig digs then. I guess I get 4. So calling it 1352 is appropriate then. Any questions? Meters per second, yeah. So I guess here, sorry that my work is a little messy. There is our final answer for part B. Okay, one last example, then I'll call it a day. One of the nifty things about this is we can actually figure out the mass of the Earth another way. Okay. We've already done a proof on how to find mass of Earth, but here's another one we could figure out. Say we wanted to find the mass of the Earth, and we know period and radius. Okay. One of the formulas I started you today with, I'm going to go back to again, Fc equals Fg. The moon is orbiting Earth, right? And because the moon is orbiting Earth, the only thing keeping it on its path is gravity. Okay. Well, how can we calculate Fc? Well, one of the ways we could do this is mv squared over r. But I actually don't want to use that one. Rather than use mv squared over r, the other way of doing this would be to take your mass and times by the 4 pi squared r over period squared. Because this is what acceleration can also be, right? I have that correct? And then force of gravity would be capital G, m1, m2 all over r squared. Okay, so let's walk through what we're looking for here. This mass right here would be the mass of the actual orbiting satellite, which would be the mass of the moon. These masses, one would be the mass of the moon, one would be the mass of Earth. Perfect, we can cancel out the mass of the moon. Now the question was, let's figure out the actual mass of the Earth. So how do you get mass of Earth by itself here? Multiply up the r squared. Now this is weird. Now the r squared, when you come up here, becomes an r cubed. Yeah. And when you divide out g, you get this formula here. 4 pi squared r cubed over t squared with g. That should be the mass of the Earth. All of these, by the way, were very easy to measure. Well, not easy to measure, but values that like could have been found out years and years and years ago. We didn't need to have NASA in the 19th century, 20th century to do this. Scientists back, in Copernicus and Kepler's day could probably figure the mass of the Earth out using this because they know pi. We just need to know how far it is from the Earth to the moon. And we just need to know how long it takes the moon to go around the Earth. And we need to know g, which is bringing me back to my first point. Finding that g value was super critical for figuring out anything that has to do with like large outer space objects. So let's try it. Let's see whether this is approximately the mass of the Earth. The radius was 384,000,000 meters, because we need it in meters cubed. And then period has to be in seconds again though. So 27.3 days. What do you multiply by 24 for hours, multiply by 60 and multiply by 60 to get it into seconds? So yeah, big number. 27.3 times 24 times 60 times 60. Square that number and then also times by 6.67 times 10 to the minus 11. Let's see what we get. Hopefully this is actually very close to what we accept as the mass of the Earth. It won't be exactly the same, but if we do it right, it should be really close.
What G value is it?
The capital G, like the 6.67 from the Cavendish experiment. All right, let's try this. 4 pi gets squared, then we times by 384,000, that was kilometers, so 3 more zeros to make it meters, and then cube that number. then divide it by 27.3 times 24 hours in a day times 60 days times 60 minutes and 60 seconds. Square that, and then also divide by 6.67 times 10 to the minus 11.
They're about the same thing.
Anybody else get this? 6.02 times 10 to the 24 for the mass of Earth. It's close. The actual mass of the Earth that we've calculated, now keep in mind, we can't actually take Earth and put it on a scale. That's not actually physically possible. But indirectly, we've already calculated it once, but here's another way of trying to calculate it. The accepted value we use is 5.97 times 10 to the 24. Ignore the times 10 to the 24. We actually think it's 5.97. So like ignore this and ignore this. Would you guys not agree that 6.02 is ridiculously close to 5.97? Like if this was a lab that we were doing, we would say this was a successful lab. Why is this value slightly off? Well, a couple of reasons. One, we just proved with Kepler's laws, or just talked about with Kepler's laws, that things don't actually go around in perfect circles sometimes. They go around in slightly elliptical orbits. So that kind of throws things off a little bit. Pretty close though, especially for high school physics at this point. That makes sense? Okay, quick summary and then I'll stop talking. I need you to know basically two skills from today. One of the skills I need you to have is that occasionally to solve a problem, you have to do this. You have to make FC equal to FG. And in doing so, you have to rearrange and make your own formulas. Okay. This last example we solved for mass of Earth. But in one of our first examples, we rearranged to solve for velocity. Okay. Occasionally, that's a skill you need to solve a problem. Make the centripetal force equal to another force and rearrange. The other skill I need you to have is to be able to solve questions about Kepler's law. And Kepler's law is pretty straightforward. It's this guy right here I need you to know mostly. Can you find a k value based on period and radius? And then if you have that k value, could you use it to find either the period or radius of another satellite orbiting it? The question I'll ask you is pretty much always going to be this question right here, where there'll be two things orbiting a planet. One of them you'll know about. Use the one to find k. Once you find k, solve for the other orbiting object. Jack?
With K, it doesn't, you could do it with seconds over astronomical units as long
Sure.
as you do it with.
So long as you keep your units consistent, it doesn't matter. The only reason astronomical units was developed was that if you're talking about things orbiting the sun, which there's lots. There's all the different planets we have, right? It makes more sense just to make k be 1. But if we wanted to, we could have had k be in meters per seconds, or days per meters, or get what I'm saying there? Hours and kilometers. So long as you keep your units consistent, that's all that matters for k. Any questions? Okay, tomorrow we're going to do a lab. Thursday I'll give you your assignment. In the meantime, if you need something to practice, here's kind of the stuff we've been working on so far. So if you're looking for something to work on, the most recent stuff is page 286. So, other than that though, we had about 15 minutes left. So, one last thing. When can I give a due date for our lab so I can start marking it? Are many of you guys finished or close to finished? When did we do it? It was last week, Thursday? Okay, how about this? Can we say by end of day Friday?